But good afternoon again, everyone, for another session. Welcome to double square moments and bounds for resonant sums for cusp forms. Our presenter today is Praneel Samanta from University of Iowa. If you have any questions for the presenter during the session, please feel free to enter those into the chat at the bottom of the Zoom room screen, and we will address them at the end of the talk. So on that note, I'll go ahead and hand it over to you, Praneel.
Thank you, Sydney. Thank you for the introduction, and thank you to the organizers and Fox Learning for this opportunity. Okay, so I have changed the title a little bit because I wanted to talk more about the background than about my particular research. But towards the end of the talk, I will be talking about my research, which I have done this year along with Tim Gillespie and Yango Ye. And Yango Ye is actually my advisor. So I'm a fifth-year graduate student at the University of Iowa. And so the thing that I'm going to talk about today is actually a pretty new field in analytic number theory. Not exactly a field, but the term that I'll be talking about over here is something which is pretty new. Okay, so I'm going to start with the background, and the thing that we are going to consider first is going to be the upper half plane, which is the complex plane where the imaginary part is strictly more than 0. And the group SL2Z acts on this upper half plane by this group action, where if the element in SL2Z is A, B, C, D, that matrix, then Z goes to the Mobius transform, which is AZ over B over CZ plus D. Okay. At any point, if you have any question about any of the things that I'm talking about, please let me know. All right, having these group actions of SL2Z over H, we define certain functions called the holomorphic cusp forms. Holomorphic cusp forms are actually holomorphic functions from the upper half plane to the complex numbers. These are holomorphic functions such that they have these two properties over here. The first one says that if I act on AZ plus B over CZ plus D, which if you remember is the action of the matrix ABCD on Z, that's going to give me this one extra factor over here. And you will see that there is a K term arising out of nowhere. This K is something that we call the weight of this holomorphic function. You might have seen this in other language as a modular form on SL2Z. They are the same thing. So, oops, I want to erase what I have drawn over here. All right. And the other thing that I need, which is something that makes it a cusp form, is that it becomes 0, it decays as my complex entry goes to infinity. So if my y goes to infinity, it's gonna decay. That's the other part of something being a cusp form. Now, any holomorphic cusp form has a Fourier expansion of this form, where these lambda fn's are the coefficients of this fz. Just a quick notation thing over here, ENZ, or if I write EZ, I actually mean e raised to 2 pi IZ. Okay, if you haven't seen this before, this is what I mean by EZ. It's e raised to 2 pi IZ. Okay, and you can see that the sum over n starts from 1 because it's a cusp form. So the constant term will become 0 when I look at the Fourier expansion of this. All right, let's move on. So far we have defined a holomorphic cusp form which has these lambda fn's over here, as the coefficients. Now we use these coefficients to construct something called L functions for these holomorphic cusp forms. So this is an L function. We are defining the LSF as sum of lambda fn over n raised to s, where n is all natural numbers. If you think that you haven't seen these kind of functions before, you might be wrong, because this is, if you just change the lambda fn's to all 1, you get 1 over n raised to s, where n is more than or equal to 1. This is just the Riemann zeta function. So this is zeta s. Oops, I didn't want to meet. Yes, that's what I meant. Okay, so these L functions are basically generalizations of the Riemann zeta function, where these lambda fn's are not 1, and these lambda fn's come from these holomorphic cusp forms for our case. And it is well known, and you can also prove this if you are an undergraduate student in analysis, you might be able to prove that this is actually absolutely convergent when real part of S is strictly more than 1. So studying these L functions are very important, because if you know something about the zeta functions, you will know that studying the zeta functions tells us a lot about prime numbers, because there are alternate formula. There is an alternate formulation of the additive structure of the L function in terms of primes. Okay, let's move on to something a little bit more complex than this. So over here, we were looking at an L function attached to only one holomorphic cusp form. What if we have two holomorphic cusp forms? Then there is a convolution operation then that we can do that will give me a different L function. So over here we start with two holomorphic cusp forms, F and G, and let their corresponding weights be K1 and K2. Okay. So given these two, I wrote defined over here, but it's not actually a definition. It's a construction from a convolution. But for the time being, we can say that we define a Rankine-Selberg L function like this, where this zeta 2s is actually the Riemann zeta function. This is the Riemann zeta function, and this is the rest of the term. And you see the lambda fn and lambda gn you see over here. These lambda fn's and lambda gns are actually the coefficients of the holomorphic cusp forms when we write them out into Fourier expansions. And like before, this also is absolutely convergent for a real part of a strictly more than 1. There should be a way for me to erase this easily, but I can't. Yeah, I'm not being able to erase it in one go for some reason. That's fine. Let's just do it one at a time. All right, let's move on. So any questions so far? This is the setting so far. These things are well studied and well known to researchers, but there is one single term that I'm going to talk about here now, that I'm going to introduce, which is going to be the central topic of this talk, which is the resonance sums. So for resonance sums, we take two real numbers, beta and alpha, where I restrict beta between 0 and 1, and I take alpha as not equal to 0. And we take phi, which is a smooth function with compact support in 1 to 2. Given this setup, we define the Sx Fg alpha beta as this sum, lambda fn, lambda gn, e raised to 2 pi I alpha n raised to beta phi n over x. Just a few words about the sum. This coefficient, this weights actually come from the Rankine-Selberg L function that we talked about up here. That Rankine-Selberg L function that I talked about. So I don't need to erase these markings I'm making. They just go along with the thing. Okay, awesome. That's good to know. And this phi we use over here, the fact that phi as a compact support between 1 to 2 controls the sum, doesn't make the sum too big over n, because I have an n over x. So n actually is restricted between x and 2x. The sum is restricted between x and 2x. Why do we do this? We do this in order to understand the oscillatory behavior of the coefficients lambda f and lambda gn. So if we can understand these kind of sums, Sx's, we will be able to say a lot about the Rankine-Selberg L functions. And therefore, we can go on to talking about the individual L functions as well. All right, so let's look at the history a little bit. As I said, this is a very recent subject. So this came first in 2000 in a paper by Ian H. Liu and Sarnak, where they studied sums of this form. I'm highlighting this over here. If you look at this sum and contrast with the sum that I wrote over up there, I'll just want to show it one more time. If you contrast these two sums, you will see that over here you have a lambda fn and a lambda gn, but over here you have just a lambda fn. And this f that they considered was a Hecke eigenform normalized, and they studied this when when alpha was 2 square root q and beta was 1/2, and q is a natural numbers. Now, After that, a lot of work has been done on these things for different cases, for holomorphic cusp forms or for mass forms. Mass forms, by the way, are the non-holomorphic side of these cusp forms. So the mass cusp forms I write over here, I'll be talking about here, are the non-holomorphic cusp forms. Okay, so this was started in 2000 by Yonish Dusanek, and I'm just going to talk about a few of them. Ren in 2010 studied the same thing for SL2Z once again, but with no restrictions on alpha and beta. Sunwoo did the same thing for mass cusp forms in 2014. Renew in 2014 actually did this for mass cusp forms as well for SL2Z, which I haven't written over here. But this is very important that the SLMZ cusp forms have been studied in 2016 by Ren and Nguyen. Okay. Now, so far, you have been seeing just one form being used, one function being used, just one lambda thing. For the first time, Zarnacki in 2016 worked with two forms, and one F and a G. And he showed that if I am looking at this, that this SX term, he showed an upper bound. He showed that the main term of this has an upper bound which is bounded by x raised to 1/8 plus 1/2. So for somebody who is working on these SXs for Rankine-Selberg functions, what we call the resonance barrier that one would like to break is this x raised to 5/8. So this is breaking this is the goal, one of the ultimate goals of these kind of projects, this kind of works. I will quickly, so the talk is going to get more and more technical with time, but we'll see how far we can go. We have 7 minutes of time. Yes. All right. So these Hecke eigenforms, okay, so these mass cusp forms, there is something called Hecke operators, and they are eigenforms for that. These forms actually form a vector space, and we consider this vector space where each of the first Fourier coefficients of these forms have been normalized to make it equal to 1. I'm just writing this in order to write this expression. I can even just not mention that as well. Okay, so following Sarnak's work, which comes from 2000, this is a standard way of studying these SXs. We don't just look at the SX, we look at it squared, and then we look at an average sum over this K1 and K2. For this, we use the G naughts, which are smooth functions from -1 to 1. That's given over here. And G0 at 0 is equal to 1. Okay. So instead of studying individual SXs, we are going to study these kind of averaged out sums over SX squared. So what's the goal in here for us? For this presentation, the goal that I'm going towards is this. So if you remember SXs, and for people who do number theory over here, you will understand that by using the Delign's estimate on the Fourier coefficients of these cusp forms, I can get a trivial bound for this SXs, which is x raised to 1 plus epsilon. So to break this bound of x raised to 1 plus epsilon is our main goal. Just a note of caution here that this bound has been broken in history. Like history has seen in the last few years, a couple of times, if in Zarnacki's 2016 paper, you will find good bounds over there. But all of those were when F and G were both fixed. For this work that I'm presenting over here, F and G are both, their weights are both going to infinity. So this work hadn't been done before. And this is a new work that way. Okay, so let's talk about the main theorem now. So the main theorem had a couple of cases over here, but I have mentioned the two most important cases. And this is the end thing, like the main thing of this talk. So the end product is, okay, first of all, if you haven't noticed, the sigma K1, L1, K2, L2 is actually this sum. Let's go back, this sum that I mentioned, the averaged sum over SX squared. that is sigma K1 L1, K2 L2. What Tim Gillespie, Yango Ye, and I have managed to do this year is for this case, so the two cases that I am talking about over here, you can see that if K1 L1 and K2 are both large enough, then this has a bound of K1 L1 K2 L2 x raised to 1 plus epsilon. And for another case, which is a non-diagonal case, as we will call it, which is a little bit more complex case, we got this one extra term. See, these two are the same thing because our K1 is equal to K2 over here. So these two are the same. These two are the same. This one extra term is here. What are the consequences? Why? How is this work important? What did we achieve from this, from doing this? Look at the first line. Let's say this is the first line, second line. Look at the first line. I will try to put both the things in one single page if possible. Okay, I can't. That's fine. So look at the first line. The bound was K1 L1 K2 L2 x. Forget the epsilon. Just I mean, you can talk about the epsilon as well. K1 L1 K2 L2 1 plus epsilon x raised to 1 plus epsilon, right? The number of terms in the sum is exactly K1 L. I mean, it's K1 L1 K2 L2. So the average size of Sx becomes x raised to 1/2 plus epsilon. Is that clear? So the bound we had over there was K1 L1 K2 L2 x. So the average size of Sx squared becomes x raised to 1 plus epsilon. So the average size of Sx becomes x raised to 1/2 plus epsilon. And this happens when K1 L1 and K2 are both large. So we get a nicer bound because the bound that we were trying to break was order of x raised to 1 plus epsilon. So we came from 1 plus epsilon to 1/2 plus epsilon. That's a good square root saving. This is for one case. And the other important interesting case, which I talked about, the second line had that one extra term. That one extra term is an ugly term because it doesn't allow us to find a non-trivial bound for Sx in average or uniformly. But what it does is it's still a good bound because it gives us a non-trivial bound for the single square moment. Recall that in that term, we were changing both f and g. Both f and g were changing. Now I'm just averaging over one form, just f. If I just completely ignore my g, I get this bound, which is a new bound and a non-trivial bound. So this is also really good for us. Okay, I don't think I have too much time remaining, maybe just 2 minutes. So what I'm going to do in the last 2 minutes is just give you an idea of what are the tools that we have used. So the rest of the part is, more involved, but I'm not going to go over that. So let's just highlight the tools I have used. The first thing that I have used is the Peterson trace formula. They have been used a couple of times. To get some expressions, we have a diagonal term, non-diagonal term. Let's just focus on the tools. So Peterson trace formula is one. Peterson trace formula is one. What else have we used? We go down, we go. We came across an oscillatory integral at one point, and there we had to use the asymptotic expansions of oscillatory integrals, which comes from the work of Sarnak and Salazar-Ye. These are also very standard ways. If you have seen subconvexity problems of L functions, you have seen such kind of things before. So that's the second tool that we use. The other tools, let's go even further. We have used Poisson summation. That's our third tool. We have used our two-dimensional second derivative test, which was developed by Srinivasan. That is our fourth tool. And the fifth tool that I will mention over here is the first derivative test, which comes from Mackey-san and Ye. So this is the fifth tool. And these are the tools that we have used to find these bounds. And yeah, so this hasn't been published yet, but hopefully in the last couple of weeks, we'll be done writing this paper and it'll be good to go. Thank you.
Thank you so much, Praneel. We appreciate that wonderful presentation. If anyone does have any questions at all, feel free to input those into the chat, or you could also ask out loud. We do have about 5 minutes into the next presentation, so he would be able to take those. And the next presentation is going to start in just a few minutes. I am putting the links to each of those in the chat right now, so you can go to the different Zoom rooms or stay in here for the next presentation. But thank you so much again, Praneel, for that great presentation and all of that.
Thank you. Thank you.